Hi, Physics 30s. I wanted to dive back into this because I didn't do it. I tripped on it, and so I cut that part out of the first video. So I'm going to now go back, and I really want to explain this mass in MeV over c squared. This will actually help you make sense of your formula sheet as well. Because if you look on I think it's on, well, whatever, you look on one side of your formula sheet, it has the masses of subatomic particles, but it has them in these units, mega electron volts per c squared. And having that as a baseline makes it much easier to compare masses rather than using kilograms. So I want to attempt to explain that, and then I want to determine the mass of an electron in mega electron volts over c squared. This table says it's 0.511, so we're going to see if we can get close to that. Okay, so here's the thought process. These basically nuclear physicists decided to come up with a convention to more easily compare the masses of these subatomic particles rather than using kilograms. Kilograms is really annoying. It's super tiny. The electron is times 10 to the negative 31. The convention uses Einstein's equation, E equals mc squared. So I have that written down here. Their target was this. We could express mass in terms of energy divided by the speed of light squared. And if the energy was in joules, okay, so if this was in joules and the speed of light squared, of course, is a meters per second squared, then you'd get mass in kilograms. And that just wasn't the useful side of it. So using the energy in joules would just give you kilograms, and then it's really not that useful. What they realized though is let's change the energy, the amount of energy in joules, let's change that to mega electron volts. Then you can't really divide it cleanly. Like you can't divide mega electron volts by meters per second squared and get, well, you're not going to get anything. You're not going to get kilograms, that's for sure, because the units don't cancel out. You never had kilograms to start with, and so you basically get a unit of mass that can't be broken down anymore, and but it's more useful as a comparative ratio. Okay, so I want to hopefully help you see that we can get that fairly easily. Okay, so here's how they do it. What you do is you first off, you determine what the energy is in joules first, and then convert that into mega electron volts. And then you just stick that energy into this expression, which you can't solve anymore. Like you can't divide mega electron volts by the speed of light squared. You can't do that and get any unit that makes any sense. So let's just do it for the electron. So the electron, we're going to take the mass of the electron, 9.11, 10 to the negative 31 kilograms, times that by the speed of light squared. We're effectively pretending that we're, annihilating an electron, okay, if you will. How much energy, what is the equivalent in energy for an electron using the speed of light squared, or using Einstein's equation, okay? So this comes to 8.199 to the negative 14 joules. Now, we're going to take that amount. I guess I could have just used that, but and we're going to convert that into electron volts. So we have to divide that by 1.6 to the negative 19, because that's how many joules there are in an electron volt. So here, let me move this up a little bit. Okay, and but we also need to, or they found that it's even better if you convert that electron volts into mega electron volts. So 1 times 10 to the sixth electron volts, or 1,000,000 electron volts, is the same as a mega electron volt. Or mega is, sorry, I'm writing over top of that. 1 MeV is the same as 1 times 10 to the sixth. Okay, so we got to take our original amount. I still have mine in your calculator. Divide that by 1.6 to the negative 19. Okay, and then divide that by 1 million, or 1 times 10 to the 6. And lo and behold, we get 0.512. Now, I guess I should say that is mega electron volts. So look at this number here. Woohoo. In fact, I think even on your formula sheet, I think they do have 0.512. If you use a more accurate number, like with more significant digits, back in this stage right here, if you see me circling that, that's actually a little more specific. We could probably get 0.511. So, but anyway, sorry, I guess I'm not totally done. All I did was I found what the energy equivalent was of the mass in mega electron volts. Okay. But then, as I mentioned, if you're now going to express mass in terms of E over C squared, we have to just leave it like that. So it's 0.512 MeV over C squared. And you can't calculate that any further. So, but this enables you to have the nice comparative ratio, and look at that. See, so that's what all of these are. So you can see, an electron neutrino. These neutrinos are really, really small. They're way smaller than an electron. But yeah, muon, this this muon, sorry, is yeah, that's the one that's over 2 times greater than the electron. The tau1, that's a beast compared to the electron. And so anyway, yeah, you can start to compare all of these particles, even the proton and the neutron, relative to all the other particles. It's easy to see their size. Okay, so you may need to actually calculate the mass of something in mega electron volts. And I don't want you to trip on it. I think it's pretty straightforward. You first off find the mass in kilograms, whatever it is, multiply that by the speed of light squared, and then convert that, which is going to be joules, into mega electron volts. And then expressing mass then becomes energy over the speed of light squared, which is MeV over C squared. Okay, so yeah, that's all I wanted you to know about that one. So anyway, add that to your other videos. Okay, keep up the good work, you guys.